This resource is the second in a three-part series on polar coordinates. Part 1 defines polar coordinates. We consider how to convert from rectangular to polar coordinates and look at examples. We also discover how to convert from polar to rectangular coordinates and look at examples. Part 2 considers complex numbers. We consider the complex plane and how to graph complex numbers. We consider the polar form of complex numbers. We discover how to convert back and forth between the rectangular and polar form for complex numbers, and look at multiple examples. Part 3 looks at De Moivre's theorem, which provides a method for raising a complex number to a power. The theorem is formally defined. We then solve examples, both for complex numbers given in rectangular or polar form. Recall that we use I to represent the imaginary unit, defined as the square root of -1. A complex number is a combination of real and imaginary numbers. In rectangular form, the complex equivalent of Cartesian coordinates, any complex number z has a form that looks like z equals a plus b times I. When we graph complex numbers, we have to consider the complex plane. Instead of x and y, we think about the real and imaginary parts of the complex number. Instead of an x-axis, we have a real axis. Instead of a y-axis, we have an imaginary axis. How exactly would we use these definitions to graph complex numbers? So we want to graph some complex numbers. The real part works like the x value from our Cartesian point and tells us how much to move right or left from the origin. The imaginary part works like the y value from a Cartesian point and tells us how much to move up or down from the origin. Let's figure out what points we have plotted on this graph. Our point is 2 spaces to the right and 3 up from the origin. So we have the complex number z equals 2 plus 3i. This point is 1 space to the left of and 2 up from the origin. Therefore, we have the complex number z equals -1 plus 2i. Here, we are 4 spaces to the right and 1 down from the origin. We have the complex number z equals 4 minus I. We are 5 spaces left of and 4 spaces below the origin. We have the complex number z equals -5 minus 4i. This point was 3 places to the right of the origin, but did not move up or down. It has no imaginary part. It is the complex number z equals 3. We have moved 5 spaces up, but we did not go left or right. Our complex number is z equals 5i. Much like Cartesian points, there is a polar form for complex numbers. In fact, the basic setup is identical. We consider the distance from the origin, which is the absolute value of the complex number, and the angle from the positive real axis, which we will call theta. The polar form of complex numbers is therefore z equals the absolute value of z multiplied by the quantity, the cosine of theta, plus I times the sine of theta. The development for converting from rectangular to polar form for the complex number is identical to that for Cartesian points. We consider the right triangle formed by legs with lengths a and b, hypotenuse with a length of the absolute value of z, and containing angle theta. The absolute value is the distance from the point to the origin. So we have the absolute value of z equals the square root of the quantity a squared plus b squared. The tangent of theta is equal to the ratio of b over a. So theta equals the inverse tangent of that ratio. As with Cartesian points, if the real part is negative, we add 180 degrees to that inverse tangent. Let's see an example. Suppose we have the complex number z equals -1 minus I times the square root of 3. The I is in front of the square root simply to avoid confusion. With this complex number, our value for a is -1, and the value for b is negative square root of 3. What would this complex number be in polar form? First, we need to find the absolute value of the complex number. We will use the formula we discussed earlier. Plug in our values for a and b. Performing the squaring, we have the absolute value equal to the square root of the quantity 1 plus 3. So our absolute value is 2. Now let's find the angle theta. Note that the real part of the complex number is negative. Therefore, theta equals 180 degrees plus the inverse tangent of the ratio of b to a. Plug in our values. Doing the calculations, we find that theta is 240 degrees. So the complex number -1 minus I times the square root of 3, when written in polar form, is 2 times the quantity, the cosine of 240 degrees, plus I times the sine of 240 degrees. What if we know the polar form for a complex number, and we want to convert to the rectangular form? Again, we follow a familiar development. We consider the right triangle formed by legs with lengths a and b, hypotenuse with a length of the absolute value of z, and containing angle theta. The cosine of theta equals the ratio of a to the absolute value of z. Solving for a, we have a equals the absolute value of z multiplied by the cosine of theta. The sine of theta equals the ratio of b to the absolute value of z. Solving for b, we have b equals the absolute value of z multiplied by the sine of theta. So the complex number in polar form, the absolute value of z times the quantity, the cosine of theta plus I times the sine of theta, equals the absolute value of z multiplied by the cosine of theta plus the absolute value of z times the sine of theta times I when written in rectangular form. Let's see an example. Suppose we have the complex number given in polar form as 4 times the quantity, the cosine of 30 degrees, plus I times the sine of 30 degrees. We want to find the rectangular form for this complex number. To convert, we distribute the 4 through the parentheses. Because our theta is 30 degrees, we can find exact values for the sine of theta and cosine of theta. The exact values for z equals 2 times the square root of 3 plus 2i. If we want an approximate value, we have z equal to 3.46 plus 2i.